Okay, hello. Just finished class in which we started using the chain rule to help us differentiate all kinds of different things that we couldn't do before. Let's continue a bit. There's one little sort of weird thing that seems maybe not so important, but is a little bit important. Let's just talk about it quickly. The ln of the absolute value of x. Now this is kind of maybe annoying or something, because every time you have absolute values in calculus, you are sort of forced to do some kind of casework. So, what happens if I try to differentiate the natural log of the absolute value of x? Well, I guess we should split this up into cases, because the definition of the absolute value says that if the thing on the inside is positive, you leave it alone. If it's negative, you take the opposite. So the very function ln of absolute value x that we're differentiating, well, if x is positive, then it's just natural log, because the absolute this is meant to be of course like that, right? The natural log of the absolute value of x. Well, of course, I can't take the natural log of 0, so therefore that's not something I'm going to consider. But the nice thing about this function is that normal natural log is only defined on positive inputs, but this number is defined on negative inputs as well. So the domain of this function is all real numbers except 0. Okay, well, if x is a negative number, then the ln of the absolute value of x is just ln of negative x. That's just simply the definition of absolute value. Okay, and then this, now that I've split it up into cases, let me take the derivative. Well, what is the derivative of natural log? It's 1 over x, as we've seen. And so that's the answer I get if x is positive. But what if x is negative? Well, then I'm following this rule. Well, this is the composite of two functions, right? The inner function is negative x, the outer function is natural log. So the derivative of the natural log of negative x is 1 over negative x back inside negative 1. Once again, the derivative of the natural log of something is 1 over the something back inside for the derivative of the something. Okay, so now the negatives cancel, and we just end up with 1 over x when x is positive, and just also 1 over x when x is negative. And so this is just 1 over x. And so, all right, this is kind of maybe a little bit boring, but we now have a rule that the derivative of the natural log of the absolute value of x is just 1 over x, kind of full stop. So this will come up in the homework, and this is just something to know. Basically, one way you can think of it is just the absolute value just goes away or something like that. This is a way of extending. What's really going on here is we're extending the definition of natural log to apply to negative numbers as well. That's kind of like what's going on. If you want to make a picture of this, you can. What does natural log look like? Of course, well, it's the inverse of of an exponential function, so it looks kind of like this. And well, great. But what if I want to now graph ln of the absolute value of x? Well, then for negative numbers, we first take the absolute value of them and make them positive, and then plug them into natural log. In other words, this is kind of like a way of making this function sort of automatically even, and we end up with something like this. So this is kind of a graph of that function, and if you use your skills from class today to try to sketch what should be the derivative of this function, you will see that here at this point 1, 0, of course, the derivative of natural log is just 1, so the slope is just 1 here, and so we have this point 1, 1, and okay, the tangent lines are huge, big, then they're 1, then they're smaller positive numbers. And so, in fact, what you end up with is this, which is just 1 over x. That's kind of what I already knew. But now, looking over here, what do we find? Well, now the tangent lines have a slope which is a tiny negative number. Now that negative number is becoming more negative. By the time I get to -1, 0, the slope is -1, and by the time I get to 0 minus, the slope is like -infinity. And so at -1, it's -1, so that's like -1. And so I have a tiny negative number and then down to -infinity. So indeed, you can think of the 1 over x function as the sort of natural answer to what's the derivative of natural log, and in some ways it's kind of like better because, well, okay, I'll stop there. All right, what about this? This is a strange and seemingly silly problem. What is the derivative of the natural log of the square root of x plus 3 over x to the 5th times sine cubed x? Okay, well, this seems like a demonic problem just designed to, you know, torture young children or to, you know, take 15 minutes and be kind of not fun. Why is this so hard? Because I'm trying to take the natural log of, well, I'm trying to take the derivative of a function which is just really complicated. And it's not just that the function's complicated, it's kind of how the function is complicated, which is sort of important, because this function is complicated in a kind of an annoying way. After all, if I want to take the derivative of the sum of 10 different functions, well, that's easily done. I just split them up one at a time and take their derivatives piece by piece. But here, we are trying to take the derivative of something that's sort of tightly, well, okay, how would you do this? I'll tell you how you would do this. What is the derivative? You'd use the chain rule. But a lot of chain rules, man. So the derivative of the natural log of something is, well, it's going to be 1 over that something. So in here is going to be this, plus 3 over x to the 5th times sine cubed x. Okay. But then I have to go back inside to take the derivative of the something. How do I take the derivative of the inside of the natural log? Well, I'm going to have to use the quotient rule, right? And, okay, I just don't even want to do this because I'm seeing how annoying this is going to be, because I have to use the quotient rule. Well, inside that quotient rule, when it comes to differentiating the numerator, I'm going to have to use the chain rule. And when it comes to differentiating the denominator, I'm going to have to use the product rule. And inside that product rule, I have to take the derivative of sine cubed x, which is going to require me to use the chain rule. So this is like a chain rule inside a product rule, and a chain rule inside of a quotient rule, inside of like a, this is like annoying. So what we're going to do is we are going to not do this. Instead, we're going to make some observations about natural log. So in a previous video, I kind of a little bit half-ass kind of reproved the basic log rules. So I mean, you really do need to know these. So the natural log of AB is ln A plus ln B. And let's see, should I just kind of do a really fast proof of this? Is this a good idea? Who can say? Yeah, maybe just really fast, right? Why is this true? Here's why this is true. Well, let's just temporarily, here's the simplest way to prove this. Let's just temporarily call the natural log of AX. And let's temporarily call the natural log of BY. And I'm going to prove to you that x plus y is ln AB. Well, the reason is like this. If x is ln A, so if x is ln A, then that means that that A is just e to the x. And if y is ln B, then that means that B is just e to the y. Okay, here I'm just sort of e-upping both sides, here I'm e-upping both sides. Okay, and yeah, so what? Well, what is then A times B? A times B is just e to the x times e to the y, and here I use an exponent rule, an exponent rule to write this as e to the x plus y. And so if A times B is e to the x plus y, then ln of A plus B is just ln of e to the x plus y, which is just x plus y. Okay, hopefully that only took like 1 or 2 minutes. So this is the kind of thing you do in a pre-calculus class, and it really is just quite simple, right? All the log rules are just consequences of basic exponent rules. And okay, maybe I'll just leave it at that. So what are the other? So this is like log rule number 1 that you need to know, and then the other one is that ln of a divided by b is ln a minus ln b. So okay, I won't prove that because you can prove it. It's very similar. And then the other one is that the natural log of a to the b is b times ln a. And this is another one that I've been using it even, crucially today in class, so hopefully you know it. Feel free to do a little bit of pre-calculus and convince yourself that this is true. And I think it's actually pretty easy. Okay, so keeping those 3 important facts about logarithms in mind, then we're going to actually erase this and do this problem, or maybe I could just squeeze it in here to this space. Because here the key is don't take the derivative right away. Instead, use the properties of the logarithm to break this function up into many tiny small pieces. And so what we are going to do is rewrite this problem as, I'm taking the natural log of a quotient, right? So if I'm taking the natural log of a quotient, then ln of a over b is ln a minus ln b. So this becomes ln of the square root of x plus 3 minus ln of x to the 5th times sine cubed x. Okay, what have I just accomplished? Well, I broke this complicated function that I'm trying to differentiate up into a much smaller function. And the big idea here is that the more little pieces you can split a function up into before differentiating, the better off you are, because it's easy to differentiate a sum of a bunch of things, but differentiating a product of a bunch of things is difficult because that's going to require the product rule and things get complicated. So I'm using sort of the power of natural log, and okay, it gets better, right? Because what is this? This is the natural log of, you should really think of this as the natural log of x squared plus 3 to the 1/2. And this natural log can be also split up into a product, right? So this becomes the natural log of x to the 5th minus the natural log of sine x cubed. So hopefully I'm not skipping too many steps here, but basically the ln of a times b is ln a plus ln b, and then I distributed the negative through. Okay, and then even just one more step, we can use this third log property that you proved in pre-calculus, that ln of a to the b is b times ln a, and so I can break this down. I can bring this down as 1/2 ln x squared plus 3 minus, well, the natural log of x to the 5th is just 5 ln x, and the natural log of sine cubed is just 3 ln sine. Okay, so I was going slowly to kind of explain what I was doing and why as I was going, but actually the process of getting from here to here is quite simple. It takes 1 minute or something like that. And what I've now accomplished is I've used natural log to break up this function into a function with much less structure. Okay, this is more fun if you do this live, but in some ways you can think of this as like a pre-digestion. So we are animals. When we eat food, it goes in our mouth and we chew it up into tiny little bits, and it goes into our stomach, and slowly our stomach breaks it up into all kinds of tiny little pieces inside of our stomach acids and whatever, and then by the time it gets down to our, I don't really know enough biology to complete this, but at some point then we, we start to like extract, individual bits of food from it. Well, okay, this is kind of like that, except before doing anything, we're going to sort of do some kind of pre-digestion. So this is more like an insect that like barfs on their food first. So I can't remember which insect it is. I guess it's like flies do this, right? So flies, they walk around and then they kind of see, oh, there's some food. And then instead of just eating it and digesting the food inside their body, they just like vomit up a bunch of stomach acid all over the food, which breaks it up into a tiny little like soup of tiny nutrients, and then they slurp it all up. And that's what we have just done. By using this natural log and its ability to break up products of things into sums of things, then we now have something that's very, very easy to differentiate. And okay, just doing this derivative just now only takes like 1 minute, because what is this? Well, it's going to be, I'm now finally doing calculus. Differentiating this becomes 1/2 times, what is the natural log of x squared plus 3? Well, it's the derivative of the natural log of something is 1 over the something back inside for the derivative of the something, which is 2x. Minus 5 times, what's the derivative of ln of x? Well, it's just 1 over x. And what's the derivative of minus 3 times? The derivative of ln of something is 1 over the something back inside for the derivative of the something. And so my final answer is going to be something like x over x squared plus 3 minus 5 over x minus 3 cotan x. And I just leave it like that. So this problem is actually not as hard as it appeared at first. I didn't have to do the product rule. I didn't have to do the quotient rule. I had to do just a tiny little bit of chain rule. And okay, great. So what is the moral of the story here? The moral of the story is when there are natural logs in your problem, you should be feeling really, really happy. And because the power of the natural logarithm is the power to break up little things into big things. And actually, I don't want this video to be too long, but it seems like, here you are in high school, and there is this kind of persistent question of like, what are logarithms? Why should I care about logarithms? What's the point of logarithms? What are they sort of good for? Why am I learning about them? And there is some tension between what and how we teach logarithms now versus 100 years ago or something like that. Because before we had widespread technology to perform calculations instantly. If you were an engineer, 75 years ago or something, you didn't have calculators. You had to do everything by hand. And you had to do perhaps, laborious calculations and how techniques for doing those calculations were very relevant to you. And it wasn't so long ago that if you asked someone in 1940 or even maybe 1980, what's the point of logarithms, they would have given you a very sort of straightforward answer. And the answer involved something about computation. So, okay, notice that if you add two numbers, it's really, really easy. Give me two numbers to add, perhaps even two numbers which are very, very big. So, 5, 1, 7, 3, 6, 9, 2, 1, etc. And then here you have, 3, 8, 1, 0, 0, 4, 4, 3. Okay, now if I want to add these up, well, there's an algorithm for adding up two numbers. You just kind of like do it, man. So you just go jump, 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 and you just add the columns. Okay, so it takes, relatively speaking, almost no time at all. And we can make this concept precise using sort of like big O notation, which is something I think you understand. If this number has n digits, and this number also has n digits, then we can analyze the sort of efficiency of the algorithm that's required to add up to n-digit numbers. And the answer is it's like big O of n. So that is to say, if your number is twice as long, it takes only twice as much time to add those two numbers. And if your number is 10 times as long, it takes only 10 times as much time to add up those two numbers. Alright, so that's like a nice, happy algorithm. On the other hand, suppose we are doing some multiplication. Now, if you're multiplying, as you learn when you are in elementary school, things are now more complicated, because what are you supposed to do? I'm supposed to multiply 3 by all that big numbers, and I get blah, 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 blah. Then I multiply 4 by that, and I get blah, 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 blah. Then I multiply 4 again, blah, 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 blah. So this is like extremely difficult and annoying. Multiplying these numbers is really, really hard. And in fact, what you're going to have to do is n individual multiplications followed by adding them all up again. And so this is like a much, much worse algorithm. Multiplying numbers is hard. but adding numbers is really easy. And so, if you want to multiply numbers, is there some kind of way that we can do this? Well, yes, there is. Logarithms can do this for you. Because the logarithm of the product of two numbers is the sum of their logarithms. And so, in an era before calculators, if you have two very big numbers that you want to multiply, instead, so suppose I want to know what a times b is. Well, instead of computing a times b, you compute the logarithm of a times b. So you have a table, and you look up the natural log of a in a table. And then you look up the natural log of b in a table. Then you add those two numbers together, because addition is basically instantaneous, time-wise. And then the sum of those two logarithms gives you the log of ab. And then you look up the, now that you have the logarithm of a times b, you look up you look this number up in what's called an anti-log table, which simply gives you a bunch of logarithms and tells you sort of what the anti-log is, otherwise known as the exponential. Okay, so the point is, historically speaking, logarithms were first invented as this powerful mathematical tool for basically turning addition problems, turning multiplication problems into addition problems. You should feel the historical connection here. If I have a multiplication problem that I want to solve, well, multiplication sucks and is really annoying. I don't want to do multiplication. But logarithms will enable me to convert via that fly vomit. We can convert a multiplication problem into an addition problem. That's kind of what logarithms do. And that same thing is happening here. The power of the logarithm in the era of calculus is the power to turn the derivative of a product into the sum of a bunch of small derivatives. Okay, I think I've made my point there. Well, that was something. I got something else for you. Suppose you give me the following curve. Y equals, now I'm just going to once again sort of be ridiculous here, so this is the sine fourth x times x cubed over tan to the fifth x times, the fourth root of x cubed plus x. Okay, every single piece of this function is something I know how to differentiate. But doing this the traditional way is going to take you, 15 minutes or something like that and be really, really annoying. Why? Well, because the general form of this thing is it's a quotient. And so I have to use the quotient rule. But inside that quotient rule, I'm going to have to take the derivative of this numerator and the derivative of the denominator. Well, the numerator is going to require the product rule, and inside the product rule, a chain rule. And this denominator, when I take the derivative of it, is going to require the product rule. And inside the product rule, a chain rule. And inside this product, another chain rule. So this is a chain rule and another chain rule inside a product rule, inside a quotient rule. It's going to be terrible. Aha! Logarithms to the rescue. We are now doing something called logarithmic differentiation. Logarithmic differentiation, loosely speaking, is a method of solving differentiation problems by introducing logarithms into the problem even when they do not exist already. So here, I saw this logarithm on the outside of my function, and if you're in the know, then you got really happy because it turns out that this problem is digestible into tiny little pieces so that the differentiation itself is easy. Well, here, I don't have a logarithm, so I just make one. In other words, take the natural log of both sides. Ah, okay. Well, I introduce this natural logarithm, and now everything is going to work out for me, because what do I get? I get on the right-hand side something which can be broken down into tiny pieces. Let's do it. And I might just like show off and do the whole thing in just like one big step, because after all, it's really not calculus, it's really just pre-calculus. So what do I know? Well, the ln of a quotient is the ln of the numerator minus the ln of the denominator. So then I have the natural log of the numerator. Well, the numerator is a product, so the natural log of a product of two things is the sum of them. but then this is also has a 4 in it, and this has a 3 in it. So this becomes 4 ln sine x plus 3 ln x minus 5 ln tan x minus 1/4 ln x cubed plus x. Okay, I'm not sure whether that was a good thing to do or a bad thing to do. Trying to keep the video short so I don't feel like showing all my steps. Also, it's just faster if you can kind of do it all in your head. But really what I just did here was apply all the log rules kind of like all at once. Right? This is really to the 1/4, so I brought the 1/4 down. This is really tan x to the 5th, so I brought the 5 down. This is tan x cubed, so I brought the 3 down. This is to the 4th, so I brought the 4 down. And then I'm starting to regret this decision to not show any work. But anyway, do this. Do this out using as many steps as you need, and you're going to get here. Okay, and now what? Now take the derivative of both sides. And here is where you need this crucial skill that we practiced today, which you still might be a little bit shaky on. So let's talk it out one more time. What is the... Maybe I should even say explicitly that I am taking the derivative with respect to x. So on the left-hand side, I'm taking the derivative with respect to x, and on the right-hand side, I am also taking the derivative with respect to x. Okay, what is the derivative with respect to x of ln y? Well, what is y after all? Y is just my temporary name for a very, very complicated function. So you have to kind of say to yourself, what is y? Y is a function. It is something that depends on x. And if y is something that depends on x, then this, taking the derivative of ln y with respect to x, is going to require the chain rule. The chain rule is needed when you take the derivative of a composite function. This is a composite function. The outer function is natural log, and the inner function is y. What is y? Some kind of function, in fact a quite complicated one, which depends on x. Okay, so the derivative of ln y is going to be, the derivative of ln of something is 1 over the something, back inside for the derivative of the something. And on the right-hand side, now we just go boom, 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 and we just do 4 quick derivatives. 4 ln sine, so that's going to be 4 derivative of ln of something is 1 over that something. Back inside for the derivative of sine, which is cosine, plus 3 times the derivative of ln x is just 1 over x, minus 5 times, what's the derivative of ln of tan x? Well, the derivative of ln of something is 1 over the something, back inside for the derivative of the something, and the derivative of tan is secant squared, minus 1/4 times the derivative of ln of something is 1 over the something back inside for the derivative of the something, and the derivative of x squared plus x is 3x squared plus 1. Okay, so what do we find here? We find that the answer to this problem is in fact, just buying myself some more room, is in fact, well, you multiply through by y, or you bring y over to the other side. What is y? Oh, it's just this. So the answer to this problem is sine to the 4th x times x cubed all over tan to the 5th x times the 4th root of x cubed plus x. That whole thing times just this stuff. So 4 cotan x plus 3 over x minus, does that simplify nicely? Sine over cosine, 1 over cosine squared. I guess I can cancel the cosine. So that's like secant over sine or some crap like that. I don't really feel like doing this. Sine over cosine. So it is secant over sine. Is that something? Not really. I guess I'll just leave it. So 5 secant squared x over tan x minus 3x squared plus 1 over 4x cubed plus x. Okay, and I probably did that correctly. Okay, what's the moral of the story? This was still a little bit annoying, but this took us like 3 minutes as opposed to like 20 minutes. And what is logarithmic differentiation? Logarithmic differentiation is, like I said, it's the introduction of logarithms into a problem so that we may employ the decompositional sort of nature of logarithms. We're letting logarithms do to our calculus expressions what they were invented to do to solve arithmetic problems, which is turn sort of products into sums, and they turn exponents into products, they turn products into sums. Okay, good. Back in, should I come back in a second for a little bit more, or should I just, I think I'm just going to finish. And just keep the video rolling. So there is about one more kind of problem to do. And maybe I'll just leave this up on the board. I know I sort of partially erased it here, but not too badly, because I would say that this category of problem that I just solved, I would call it logarithmic differentiation optional. And I'm calling it logarithmic differentiation optional because technically speaking, I didn't have to use logarithms because I could have done it out the long way, even though that's to be discouraged. But then there is a sort of a different category of problem, which is logarithmic differentiation not optional, so mandatory. And that's if you're trying to differentiate a function which is in fact a function to another function. Okay, this is kind of maybe a weird thing to do on video instead of live, but okay, take this function, y equals x to the x, and well, what is this function? So this is kind of crazy. This is a sort of a new function that you've never seen before in your whole life. And there is a reason why you never saw this function before in pre-calc. That's because it's crazy, and actually without calculus we can't even barely talk about it. So alright, I think the first important thing to realize is that this function is not a function that you have seen before. And okay, this comes up in calculus sometimes, that people get all a little bit confused between the various different kinds of functions. So let's kind of have this out right now. This is sort of a silly thing that I do live, maybe, but let's just do it now. So what I'm about to do, I don't even want to write it on my whiteboard, because if I write it on my whiteboard will cry out in pain. So I want to write it on this board. And what I want to sort of explain to you is that, you have these rules, right? What are the rules? You have power functions. Well, what is a power function? A power function is a function of the form x to the n. And we know how to differentiate functions of the form x to the n. It's nx to the n minus 1. Okay, we've been talking about this forever. But, in a very superficial level, power functions are of the form, something to the something. We also have exponential functions. Exponential functions. And what is an exponential function? It's a function of the form a to the x. And okay, today in class, we did it the case where a is 2, but today in class we determined that the derivative of a to the x is ln a times a to the x. In other words, exponential functions are these sort of very important functions which have the property that their derivatives are also exponential functions. Every exponential function grows exponentially. Okay, so these are two very different things, and people who are not mathematically sophisticated perhaps do not appreciate the difference between them, but they are very, very different. Note that in a power function, it's this number, x, which is getting bigger, but the number of times x is being multiplied by itself, so to speak, that number is staying fixed. So these are polynomials if n is a positive integer, and if n is something else, there's something else. But here, with exponential functions, it's the base which is staying the same, but it's the exponent which is growing. Okay, so there's even some kind of thing on Blair Bash with me and Kaluta fighting about this because he was calling some cubic function exponential, and I was like, no, it's not exponential. The point is that someone somewhere in America every day makes a horrific mistake, and here's this whiteboard now. They say, okay, what's the derivative of 2 to the x? And what they say is, hopefully you guys can read that. What they say is, oh, it's just like, it's the power rule. It's just x 2 to the x minus 1. And then what happens is the universe shrieks in horror. That is just completely not right. It's just wrong. It's wrong. That's just not true. Exponential functions are exponential functions, and power functions are power functions, and they're two very different things. X to the x is yet another different thing. So this is not an exponential function. It is also not a power function. What is it? It's its own kind of thing. And therefore I can't follow some sort of known rules or something. Okay, how can I deal with this? Well, we have this variable sort of up here, up high up in the tower, as I was saying earlier today. And the only way to rescue a variable that's stuck up in a high tower is to use logarithms. So you use logarithms to kind of rescue the princess. So here, unable to differentiate something of the form x to the x, I introduce logarithms and I take the logarithm of both sides. And if I take the logarithm of the, and what is this? Well, I guess I can do this in multiple lines. And then what is this? This is, of course, x ln x. Okay, so now I took the logarithms of both sides. Just like before, I introduced logarithms into a problem where they did not previously exist. I used the rule for logarithms to bring that x down. And now I'm going to differentiate both sides with respect to x. So here I'm going to take the derivative with respect to x of ln y, and here I'm going to take the derivative with respect to x of x ln x. Okay, what is the derivative with respect to x of ln y? Answer, 1 over y back inside dy dx. And what about the derivative over here on the right? Well, now I have to use the product rule. So it's the derivative of the first, which is 1, times the second, plus the first, x, times the derivative of the second. And the derivative of ln x is 1 over x. And so what I get is that dy dx is y, I multiply both sides by y, so in other words, x to the x, times ln x plus 1. Okay, so this is once again an example of logarithmic differentiation. But it's an example of logarithmic differentiation in which you really can't do the problem without logarithms. So you sort of have to introduce logarithms. Okay, let's do one or two more quick examples of this. Let's erase this. And while this thing is up here on the board, let me mention that just like in class today, if you're still finding yourself kind of weirded out by logarithmic differentiation, there is another method, but it's kind of more, it's weirder, but maybe you like it better, I don't know. And the idea here is that, so now I'm just redoing the same problem in a format that's slightly different. So, okay, I want to take the derivative of x to the x. That was the problem after all, right? So never mind all this y stuff, that was just a distraction. Let's just do the problem. Well, how do we do the problem? Well, you need to sort of bring that x down. And so what you're going to do is you want there to be a logarithm in there. But you can't just have a logarithm of something just because you want it to be there. And so you raise the whole thing, you put the whole thing in the power of e. In other words, you use the fact, and here I'm really assuming that you have a solid basis of pre-calculus understanding between the relationship between e and the natural log function. They're inverses of each other. And so, e to the natural log of anything just is that thing. That's what it means to be an inverse. Okay, so I replace x to the x with e to the natural log of x to the x. Why would I do such a strange thing? Well, because now I can write this as I can now sort of inside the exponent of the e, I can apply a log rule. And this becomes e to the x ln x. Cha, cha, cha. And now I'm going to differentiate. And this is sort of like one thing that's up there. So now I have to use the chain rule, because chain rule says that the derivative of e to the something is e to the something back in time for the derivative of the something. So what is the derivative of e to the x ln x? Well, it's e to the x ln x back inside for the derivative of x ln x, which we've already seen, right? This requires the product rule, derivative of the first x times the, derivative of the first, which is 1, times the second, plus the first x times the derivative of the second. Derivative of ln x is 1 over x. And now I do a couple of things. I sort of pop that x back up. So it's done its job now, and so now I sort of re-put it up there. Well, I just apply the log rule kind of in reverse. And then what's here? This is just ln x plus 1. And then, of course, e to the ln of something is just that thing. And so, indeed, I get the same thing as I got over here. I guess I erased it. But anyway, this is the exact same answer I got above. And the only difference is that I didn't, I would still call this, broadly speaking, logarithmic differentiation, but it feels different because I only have, I'm doing the whole thing only in terms of just one variable. So generally people don't like this, they find this kind of weird, so normal people do it this way. Okay, good. So now two more things. So I guess I have two sort of options now. I could do one more example of this, or I could just do it in general. Maybe just doing it in general is kind of nice. Because what really is happening here? What's really happening here, ultimately, I used my example x to the x, but really x to the x is just the simplest possible example of a more general phenomenon. And the more general phenomenon is, what do you do when you're taking the derivative of a function which is in the form a function to a function? Okay, and so you could call this something. I don't even know what to call this. It's not the product rule. It's like the exponent rule or something like that is really what it is. What do you do when both... What do you do when you have one thing raised to the power of another and both of them are growing? And, okay, the answer is you use logarithmic differentiation. So you take the natural log of both sides, and when you take the natural log of f to the g, then you get, by a log rule, g of x times the natural log of f of x. And then you take the derivative of both sides with respect to x. And that's that. And over here, I have to use the product rule. So what's the derivative of ln y? Well, it's 1 over y back inside for the derivative of y, which is, with respect to x, which is dy dx. And how about differentiating this side? Well, I use the product rule. Derivative of the first is g prime times the second is ln f of x plus the first is g times the derivative of ln f of x, which is 1 over f of x back inside for the derivative of f of x, which is f prime. So in some ways, there is a kind of a general rule for this. What is our overall answer? Our overall answer is that the derivative of f to the g is f to the g times the derivative of g times ln f of x plus f prime g over f. Okay, I have never seen this formula ever written in a textbook ever. No one would ever write it down. No one would ever memorize it because it's kind of too annoying. And honestly, this is going to come up like, I don't know, like 3 times ever again in the rest of your life. So it's not that important. Therefore, people don't encourage you to sort of learn this formula. Instead, what you really learn is like the method. And the general method is, you know, use logs and bring that thing down. Okay, the final thing, and I guess this is kind of optional, so if you want to turn this off, you can just turn this off. The final thing to do is to tie up our last kind of loose end. I think it's our last loose end. That, recall that, you know, going back already 2 weeks now, I told you to just trust me or whatever, that the power rule works for non-integer exponents. And you have been, for the past 2 weeks, differentiating x to the 5/3 as 5/3 x to the 2/3, and you're just trusting me that that this formula is applicable. And the reason why we did it that way is because our book just did it that way. So I just followed along. And the reason why we didn't put in a lot of effort back then to prove this properly is because once you know the chain rule, the proof is very, very fast. And the answer is you do it logarithmically. So it's like this. Well, okay, there's actually even many ways to do this. But suppose I want to differentiate x to the, I'll just say p over q. So at the moment, I'll just deal with the case where this is rational. So what is this supposed to be? Well, if we trust the product rule, the power rule, what's supposed to happen? The answer that we were told is that this is supposed to be p over q times x to the p over q minus 1. So is this true or not? Well, this now becomes kind of trivial because, watch. You write this as y equals x to the p over q. And then you just don't want that p over q up there because it's kind of annoying. So you just take the log of both sides. So you get ln y equals ln of x to the p over q, which is just ln y equals p over q ln x. And then you differentiate both sides with respect to x. What do you get? 1 over y back inside dy dx. And this is just p over q times the derivative of ln x is 1 over x. And so, what is the formula therefore? dy dx is y times all of that. But what was y? Y is just x, well, maybe I'll even write it. It's y times p over q times 1 over x. But otherwise known as p over q times y is just x to the p over q. And if I divide that by x, then I get exactly the thing I was expecting. P over q x to the p over q minus 1. And in fact, if you look at this proof a little bit more closely, you will see that I never even used the fact that p over q was rational. So in some ways, this proof is even more general. In other words, I've even proved the thing that you never ever see, which is like, you know, some crazy function like x to the root 3 or something like that. I don't know what kind of psychopath would ever be messing around with a function like that, but if that's the function you wanted to differentiate, then, well, the power rule suggests that the answer should be root 3 x to the root 3 minus 1, and that's just true. And the truth of that is handled by this proof here that I just gave. Okay, so what have we done in this video? We differentiated ln of absolute value of x, and we showed that ln of absolute value of x is kind of like extending the natural log function to the negative numbers. We did an example in which logarithms were involved, and we showed how you can use the log rules to break it up into little pieces. We reviewed kind of the history and original motivation for logarithms, and we reproved, at least one of the log rules. Then I introduced an example where you might want to use logarithms even when they weren't already there. Then we talked about these crazy functions which are functions in which both the base and the exponent are growing, that they are neither power functions nor are they exponential functions, but they are something else, and for these kinds of functions you have to use logarithmic differentiation. And then we tied up this loose end. So, okay, good. I believe we are now done with section 3.5, which is our book puts all of this together into one big section on the chain rule. So, alright, I'll see you all, you're going to watch this video, I'll see you all next week. Bye.